Right, this is chapter 6 from the Stats and Mechanics Year 2 book, and this is on projectiles. In Year 1, you did what we call stuff being thrown up and down in one dimension. So you would have had something thrown up like that, and maybe it came down like that. So we would have had u here as the initial speed. Up here this would be the maximum height, and one of the things you'll remember at the maximum height is that v equals 0 when you get to the maximum height. These things are symmetrical, so whatever the speed is here, this is going to be the same on the way down. If it's launched from the ground and it returns to the ground, then whatever time it takes to reach the bottom, it's going to take half the time to get to the top. So it was only ever stuff that goes straight up or down, or it was things that were projected and they went along in a straight line, and u would be here and v would be here and so on. What I've just got over here, just as a reminder, are our Suvat equations. They're in the formula book, so you don't need to memorize them, but it does save time if you know which ones to use. Now in Year 2, we step it up, we go into now 2 dimensions. So what we're looking at are things which are projected, and maybe they go up and across like that. So there's 2 bits to the motion of this particle. So we've got a horizontal and a vertical. We'll be looking at that in the next section. The first section, actually, what we'll be looking at is projection, where it's just projected horizontally. So for example, imagine like you've got like the top of a cliff here, and whereas in Year 1 something would have just been dropped from the edge of that, what we're going to get now is something is projected off the edge, and then what will happen, it will go down and it will form that sort of shape. So let's make this maybe this is the sea here, and you know it's thrown off the edge. So what we've got is we will have an initial velocity u, and that will be horizontal. We will have a displacement. How far does it go across here? We'll call that x. We will have how far it goes down. We'll call that y. Normally y goes up, but in this case, since it's going down, we'll take y is going down. What's important is that the motion of this particle has a horizontal and a vertical component to it. A horizontal and a vertical component, 2 different bits to it. So let's look at what's going on in the horizontal. Now, if you were sort of looking from above, let's say you were looking from up here, and you saw this stone or whatever being thrown across, as it went across, let's imagine you couldn't see it going up or down or going down, you just saw it going across, you would notice that the speed of it doesn't change. As it goes across your line of sight, it would be the same. It wouldn't seem to be speeding up or slowing down. That's something really important when we have projectiles in 2 dimensions, is that the horizontal velocity is constant. So wherever you measure the horizontal velocity from, let's say we measured it from this point here, there'd be a horizontal part to the velocity and there'd be a vertical part to the velocity. This part, the horizontal part, would be the same as what it is at the start. It would be u. So the horizontal velocity is always constant. Now, if the velocity is constant, you can just use speed, distance, and time, because the acceleration is going to be 0. So you could use speed equals distance over time, to work out either the distance or the time taken. So that's the first thing. The horizontal velocity is constant. Now the vertical velocity changes. So if we look at what's going on in the vertical, that changes. And the reason it's changing is because we have gravity, that acceleration going down. So that means as it drops, its velocity or its speed increases. So in the vertical, I suppose we could see that down here, what's going on in the vertical. So we have basically this going on. So S, well, S is just going to be that Y, what we've called Y. Okay, so we'll call that the Y displacement. In this particular example, since it's just being projected horizontally, U is going to be 0 because there is no vertical part to the initial velocity. There you can see there's just a horizontal part. So it's just been thrown straight across. So U would be 0. V, well, we'd have to work that out. We've got our Suvat equations to help us work those out. The acceleration, well, if we take downwards as positive, the acceleration would be 9.8. And the time's just going to be the time it takes to get to a certain point. Now, because we have a horizontal and vertical component, these need to be worked out separately, but there is something which is the same in both. If I go back to this point here, it will take the same amount of time horizontally to get to this point and vertically to get to this point. The time for the horizontal and the vertical is the same. So if I highlight the time here and the time here, yeah, those two can be linked together. Yeah, those two can be linked together. You could almost draw a little diagram like this, couldn't you? You could say, draw Suvat, S-U-V-A-T for your vertical, and then let's put that arrow on the other side over here because I'm going to write S-U-V, let's move it a bit further across so it's closer, S-U-V-A-T, and that's for my horizontal. Can you see the time is the same for both? So time horizontally and vertically is the same. So once you've worked out the time for one, horizontal or vertical, you can use it in the other. So for example, if I worked out the time it took horizontally to reach the ground over here, I can substitute that time into the time vertically it takes to reach the ground. So the time it takes to reach the ground is the same horizontally and vertically. That's what links the two, the horizontal and the vertical. So if you've only got information about the horizontal and you need to work out something for the vertical, work out the time, and that's what you can then substitute from one into the other. That links both. Acceleration isn't the same for both. The initial velocity isn't the same for both. The final velocity isn't the same for both. The acceleration definitely isn't the same for both because there's no acceleration in this direction, horizontal direction, but time is the same for both. So that will allow us to link the two together. So I'll just put up here, horizontal speed, we've written it down, that's constant. Vertical speed, well, we'll have to use our Suvat equations to do that. And the time is the same, horizontally and vertically. Okay. Right, so let's have a look at this. Any of these questions, always draw a diagram. A particle is projected horizontally, so there's our horizontal velocity. at a point 78.4 meters above a horizontal surface. So let's surface. So let's get a diagram going here. So a bit like the example that I did, it's going to be projected off there. It's going to fall down there. It tells us that this is 78.4 meters from there to there, and the horizontal projection here is 25 meters per second. Anything else on that diagram? Well, we're going to have acceleration going down 9.8 meters per second squared. Right, okay. Find the time taken for the particle to reach the surface. So to do part A, we're going to be looking at what's going on vertically, because we know the vertical distance to the surface. We don't know the horizontal distance to the surface, but we know the horizontal surface. So the first thing I'm going to do is to write out SUVAT and see what we know. Right, so we're going to take downwards as positive here, because the whole movement of this particle is downwards. It doesn't really make sense to take upwards as positive. We'd still get the same answer, we just end up with a whole heap of negatives, but we get the same answer. Right, so S, we want to work out how long it takes to do that distance, 78.4. Remember, with horizontal projection, the vertical velocity is 0. We are not interested in what the velocity is, the final velocity. The acceleration, because we're taking downwards as positive, is going to be 9.8, and we're trying to find the time. So I'm looking for an equation that has S, U, A and T in it. So if I go to my SUVAT equations, I will find that is S equals UT plus half AT squared. So we just substitute in 78.4 equals 0 times T plus half times 9.8 times T squared. Well, the bit with the 0T cancels out, so we don't end up with a quadratic that we have to solve. So we will have 78.4 equals half of 9.8. Shouldn't really be using the calculator for this, but I will. 4.9. So 4.9 T squared. And then we'll do, we want the square root of 78.4 over 4.9. 78.4 divided by 4.9 square rooted. That's 16, so it's going to be 4. Okay, so it takes 4 seconds to reach the ground. Okay, the horizontal distance travelled in that time. Right, now what did we say is the same for both? Time. So we now have the time. Because the speed is constant, we can use just speed, distance and time. We don't need to use SUVAT. If you did use SUVAT, it would just cancel down to speed, distance and time. So for example, if we decided to use, we're trying to find the distance travelled in that time. So let's say, for example, we use the second SUVAT equation, this one here. Well, then what would happen is that both of these would be the same, U and V, they'd both be 25. And then what would you have? The displacement is basically 25 plus 25 divided by 2 is just 25. 25 times t. In other words, the displacement, the distance, is equal to the speed times the time. Yeah? The same with any other equation down here. Down this one, the acceleration is 0, so all of that disappears. That won't be particularly helpful, because you just end up with 25 squared equals 25 squared, so that doesn't help. In this one down here, all of this bit of the equation would disappear because the acceleration is 0. What would you end up with? Displacement is speed times time. Same with this one. That's 0. You'd end up with displacement equals speed times time. If we just get used to the idea that for the horizontal, we're just going to use speed, distance and time. Then it just saves time. Speed, distance, time. Okay, so I'm trying to find the horizontal distance. So we just need to take care that it's going to be d that we use for distance, not s like we use for the Suvat equations for displacement. All we need to do on this equation is the speed, which is 25, times the time that we got from the previous section, which was 4. So it's going to be 100 meters to do that distance. So let's just highlight the answers. T is 4 for the first bit and 100 meters for the second. Nice straightforward answers for that question. So here what we've got, we'll start with a diagram. So it's being projected at this point. We don't know how far it is, but we just know it's being projected horizontally, and it drops forever down here. So it's going to keep going, and we know that the initial velocity is 15 meters per second horizontally, and we're trying to find out, well, after 3 seconds, let's put t equals t, it's at this some sort of point here, and we want to know the horizontal and the vertical components of the velocity. In other words, how far across from here has it gone, and how far down has it gone after 3 seconds. Right, so we're going to have to work out the displacement horizontally and vertically. Right, so let's use S and a little x that represents the horizontal displacement. So we can just use speed, distance, time because the velocity is not changing. It's a constant velocity. So we can just do speed times time, which means it's moved across 45 meters. Right, let's now work out the displacement vertically. Now we need to use Suvat to do this. So S-U-V-A-T. S is what we're trying to find. The initial velocity vertically is 0. V we don't care about. A is going to be 9.8, so I should put my 9.8 going down there, 9.8 meters per second squared going down, and the time is 3. So U, V, A and T, U, V, A and T, oh no, sorry, let's highlight the right ones. S, U, A and T, and that's going to be S equals UT plus half AT squared. So S equals UT plus half AT squared. Let's put those in. So S is what we're trying to find, so that's the subject, that's nice. 0 times time plus half times A times the time squared. So S is just going to be, I think that's 4.9 times by 9, which is 44.1 meters. So that is the vertical displacement. Yeah, so I should write that as SY because I used SY before. So SY, 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 and I suppose I should put Y for U next to the little U here because that's the vertical displacement, or the vertical velocity, initial vertical velocity. Right, okay, so the next bit of this question is that we need to find a distance the particle has travelled. Now, the distance it's travelled is going to be this bit here. How far is it from the start point, and you can see it's just Pythagoras. Let's do part B over here. So it's just going to be the square root of 45 squared plus 44.1 squared. It's nice and easy. Square root 45 squared plus 44.1 squared, and we get 63.00642, so we can call that 63. So 63 meters. So again, 3 significant figures is how we want to give our answer. Now, if this question said the direction it's traveling in at that time, then we would still use the 45 and the 44.1, but we would do trigonometry. So you'd probably do something like the tan inverse of 45 over 44.1 or vice versa. But yeah, we just want to find the direction. So rather than Pythagoras, it would be trigonometry, tan inverse of something. Okay, example 3. So again, another horizontal projection here, and my little diagram like this. This time we do know the distance above the point of projection, and that is 122.5 meters. So that's 122.5. It's doing this motion again, like that, and falling down. The initial velocity there, horizontal velocity, is u. And it says it hits the plane, so it hits this thing at the bottom here, the plane, the ground, whatever, and it's 90 meters away, a horizontal distance of 90 meters from its starting point, which means that this distance here is 90 meters. Okay, and the question is, find the initial speed of the particle. So this is going to be a combination of horizontal and vertical. So let me just put on the acceleration going downwards, like that. Now, I can't work out, if I start looking at the horizontal information, there's not enough information for me to work out the time, because I've got the distance, yep, but the time is unknown, and the speed is unknown. So I haven't got the time to help me work out. That'd be too easy a question otherwise. So I'm going to have to use what I know about what's going on vertically to find the time that it takes to get down here, and then substitute that time for horizontal, and then I can work out u. So I'm going to start by working out the vertical time it takes to drop 122.5 meters. So we're starting and we're taking downwards as positive. We've smoothed that way. Now, so S 122.5. U, remember that's 0. V, we don't know, and we don't really care about. It's not going to help us. A is going to be 9.8. T is what we want to find. Okay, so S, U, A and T. S equals UT plus half AT squared. So let's write that down. S equals UT plus half AT squared. Now, I would always write down the equation you're going to use before you substitute in. Don't just like substitute the numbers in. Write the equation down to show that it shows the examiner, right, I know which equation I'm going to use. So even if you make some mistakes, you may get some credit for that. So 122.5, we just substitute in now. Then we've got 0 times by t plus half times 9.8 times t squared. If we work that out, we'll get 122.5 equals 4.9 t squared. So divide by 4.9, find a positive square root. So 122.5 divided by 4.9, square root that, and I get 157.87 for the time. Let's just check that. 122.5 divided by 4.9. Oh no, I don't know what I did. I think I did 122.5 times 4.9. It seemed a bit big, which is 25. Square root of 25 is 5. It seemed way too big an answer. So, like I've mentioned before, when you're sitting in an exam, you're doing some questions. When you get an answer, look at it. Does it make sense? I just did some working. The answer did not make sense. I ended up with a huge number for the time, thousands of seconds. That alerted me to go back and check my working. So that's really important you do that, because you know, sometimes students will just, whatever comes up on a calculator, they write it down without thinking, is this answer sensible? And definitely what I had on my calculator screen wasn't sensible. So I've got t equals 5. That's what I know the time is. Vertically, I can now substitute that into my horizontal. Now, we can just use speed equals distance over time. So I have the time, I have the distance. So the distance divided by the time is going to give me u. So let's write that down. U equals the distance 90 over the time 5. It's going to be 18. So there we go. U equals 18 meters per second, and it's a nice whole number answer. So let's just highlight our final answer there. Right, there's the exercise you need to do. Exercise 6A, pages 110 to 111.